There we are. Okay, so let's start. So first I'm gonna start with this right triangle trig. Okay, so we start off with just a regular right triangle. And consider angle theta inside this triangle. Okay. And let's say that this length is A, this length is B, and this length is C. Okay. So as soon as you have it, right, you define following. You say that sine of theta is going to be A over C, and cosine of theta is going to be B over C. Now notice that this is completely independent of the triangle that you choose. That depends only, because we're talking about ratios here, this is completely independent of the triangle that you choose. So if you have a different triangle, right, and let's say this length over here is going to be B1, this length over here is going to be A1, and this length over here is going to be C1, right? The ratios are going to be the same. This is the same as A1 over C1, same as B1 over C1. Okay? So it doesn't matter what triangle you choose, the ratios are going to be the same. Okay? So if you have an angle, you form any right triangle, and we calculate the ratios, and no matter what right triangle you form, the ratios are always going to be the same. Okay? And now you introduce additional trigonometric functions, which are called tangent of theta, which is going to be sine theta over cosine theta, or A over B, opposite side over adjacent side. Okay, and then you also have the three additional reciprocal functions, which is secant theta is 1 over cosine theta, cosecant theta is 1 over sine theta, and cotangent theta is 1 over tangent theta. So you need to know what these functions are. They're not as often used, but these two you absolutely have to know. This one, tangent, is you should know what it is, and this one, so tangent and secant are also used in calculus. Okay, so these four are like a must know, and these two is like you should know what they are. Okay, right. So already right after you have this, you have the Pythagorean identity. Immediately have the Pythagorean identity, which is the following. So what is the Pythagorean theorem? Pythagorean theorem says a squared plus b squared is going to be equal to c squared, right? Now, if you divide everything by c squared, you're going to have a over c squared plus b over c squared is equal to 1, right? What is a over c? A over c was sine theta, and b over c was cosine theta. So we have sine squared theta plus cosine squared theta is equal to 1. And that's the Pythagorean identity. Okay. All right. I want to do, yeah. Now, if you take this Pythagorean identity and you do yeah, sure. Yeah. Okay. So let's take this Pythagorean identity. All right. I'm gonna move it over here. All right. Since we're already know that it is true. If I divide everything by, let's say, cosine squared theta, I have sine squared theta over cosine squared theta plus 1 is equal to 1 over cosine squared theta. Sine over cosine is tangent, so I have tangent squared theta plus 1 is equal to secant squared theta. Another identity. Okay, so here we have one identity over here and another identity over here. Okay, so here are two identities that you should know about already. Okay, this is just straight up from definitions. Okay. Okay. Now special triangles. Okay. Let's see. If you take, so some triangles that you absolutely need to know are 45, 45, 90. Take an isosceles right triangle. This is 45 degrees. This is 45 degrees. If you call this length x and this length x, by Pythagorean theorem, this is going to be x squared over 2. Okay, I'm going to post this later, but okay. Is this okay?
1 second. I gotta finish this.
All right, okay. Going too fast, okay. Okay. I'm just going to stick with this for a little bit. So special right triangles. So there are two special right triangles. There's 30, 60, 90. And there's 45, 45, 90. I mean, they come. Well, 45, 45, 90 comes from Pythagorean theorem. People okay with this?
Yeah.
Okay.
Yeah.
Mr. Scholar, the triangle on this page is the tangent triangle, right?
I'm not sure. What do you mean by that?
You wrote tangent on like the page we were just on before. Like lower.
Okay. So let's assume people caught up. So if we examine this triangle, we get the following. We get sine of 45 degrees is equal to 1 over square root of 2. Cosine of 45 degrees is 1 over square root of 2. And tangent of 45 degrees is going to be equal to 1. Okay. Another special right triangle is a 30, 60, 90 right triangle. So this is x, and this is 2x, and this is x root 3 over 2. And here we have sine of 30 degrees, right? Which is going to be opposite over hypotenuse. It's going to be the same as cosine of 60 degrees. Because for 60 degrees, it's adjacent over hypotenuse, which is going to be 1/2. Sine of 60 degrees, the same as cosine of 30 degrees, going to be √3 over 2. Sorry, this has to be √3. No, there's no 2 here. Okay, and finally, tangent of 30 degrees is going to be equal to opposite over adjacent, which is going to be 1 over square root of 3. And tangent of 60 degrees is going to be square root of 3. Okay. Are we all okay with this? This is for angles inside a triangle. Okay. Can we move on? Okay. So now I'm going to give you trigonometric functions of any angle. Trigonometric and the unit circle. Okay, so what do we start with? We draw a unit circle. And then the radius of the circle is 1. Okay. Now we say that, so let's say this is radius 1, centered at the origin. And for whatever point, so now let's say that you have a ray. Right, and let's say this is angle over here, x. We say that this point has coordinates cosine x, comma, sine of x. Okay? Is it okay if I use letter x, or should I use letter alpha, or should I use some other letter? Is this okay? All right.
Sine x
So-
is okay.
Yeah, that's fine.
Yeah.
Yeah, it's fine.
So why is that? Okay. Well, let's form this right triangle over here. Okay. Let's form this right triangle over here. Okay. So this angle over here is going to be called something called the reference angle. And since the hypotenuse is equal to 1, the sine of this angle is going to be opposite over adjacent, right? But adjacent is so opposite over hypotenuse, and hypotenuse is 1, so it's just going to be this length, which is the y coordinate. And the cosine of this angle is going to be adjacent over hypotenuse. Hypotenuse is just 1, so it's just going to be this length, which is the cosine, okay? And this generalizes trigonometric functions for any angle, because now x, this angle could be bigger than 90 degrees, or it could be negative, it could be in this quadrant, or it could be in this quadrant, and so on. Okay, so we are generalizing.
Why Is y the sine?
I'm sorry?
So is the basically the y direction, is that sine?
Okay, yes, yes. So the y direction, the vertical direction is the sine, and the horizontal is the cosine. Maybe I should change this x to some other letter.
Wait, no, Mr.
Let's
Sklar.
change it to letter theta. Yes.
What about the angle inside the circle? Is that also theta, or what would you call that?
You mean this angle right here?
Yes.
Okay, so the purple angle would be called, this specific purple angle would be called 180 minus theta. But it varies, okay? Like if theta is, let's say theta is over here, then this angle would be 180 minus absolute value of theta. Because if theta is, let's say, negative, right, this reference angle would be different, right? So it depends on this angle theta, okay? But the angle theta, so sorry, the reference angle, let me just write it down. Reference angle is the acute angle between the x-axis and the terminal side of theta. Right? Okay. And the property is the following. Is that sine of theta, let's call this reference angle, let's give it the name R. So we say that sine of theta is either positive or negative sine of R. Cosine of theta is plus or minus cosine of R. Actually, probably it would be the right way to do it this way. And I hope I'm not going to confuse people. Okay, so sine, cosine, tangent of angle theta are the same in magnitude as the sine of the reference angle, cosine of reference angle, and tangent of reference angle. Okay, with the only exception that depending on where the reference angle is located, right, the sine, cosine, and tangent are going to be positive or negative. For example, let's do an example. Find sine 120 degrees, cosine 135 degrees, and let's say tangent of 270 degrees. Let's not do 270, let's stay. Let's do 180. Okay, so what would that mean? Okay, so first let's do 120 degrees. Actually, it doesn't really matter. Let's just call this angle 120 degrees. So let's say this is 120 degrees. Now the purple triangle would look like this. the reference angle would be 60 degrees, right? So the purple triangle, the reference triangle, would look like this, right? This would be 60 degrees. You know it. Right? And this is 1 over here. So then this would be square root of 3 over 2. And this would be 1/2, right? So then sine of 120 degrees would have to be equal to square root of 3 over 2, right? The y-coordinate of this point.
Wait, how did you determine radical 3 over 2 and 1?
Well, the radius of the circle is 1, right? It's a unit circle, right? And if you know that this is 120 degrees, then the purple angle has to be 60, right? Makes sense?
Wait, so then how did you determine radical 3 over 2 then?
Well, this is a third 60, 90 right triangle, right?
Oh, okay.
Okay, all right. Okay, so now let's do the next one. Enough space here. Yeah, maybe. So now let's pretend that this angle is 135. I'm not going to change the diagram, I'm just going to pretend it's 135. Then my reference triangle it's going to be the 45, 45, 90 triangle. Right, so this is going to be 45 degrees. We want the cosine of 135, so this is going to be square root of 2 over 2, square root of 2 over 2, and this is 1. So we end up with cosine of 135 degrees. It's going to be equal to negative square root of 2 over 2. Because the x-coordinate of this point is going to be square root of 2 over 2, but negative. Make sense? All right. Okay, finally, let's calculate the tangent of 180 degrees. Now that's going to take a little bit of, well, Jabeki is inside. I just let her in. All right. Okay. This one's going to be not so bad, right? Because if I want tangent of 180 degrees, 180 degrees is this angle. So we're at this point, right? So just by looking at the diagram, sine of 180 degrees is going to be 0. Cosine of 180 degrees will be equal to negative 1. So tangent of 180 degrees is naturally 0 over minus 1. which is going to be 0. Okay. Okay, so sine, cosine, tangent values at these points can be defined just from the diagram. So you don't need any right triangles for that. Okay. So these are the special right angles. So I think I'm going to assign some extra credit on delta math so that people who were here can, can do it much easier than people who weren't. But I think that's also fair. All right. All right, I know, right? Okay. Yeah, I'm not super happy with the fact that we have 4 classes, and out of 4 classes, we have what, 12 people. That's like, lame. Okay. So do we have any questions so far? Okay, so far, just to recap.
Mr. Square, I have one question for you.
Yeah.
Can you scroll back down, please?
I will. So just to recap, we have a right triangle trig, right? So where I define the the sine, cosine, tangent, secant, cosecant, cotangent, the trigonometric functions. Then right away we have the Pythagorean identity, and using special right triangles, we get sines, cosines, and tangents of the 45, 30, and 60 degrees. And then we define trigonometric functions of any angle on the unit circle. So we use unit circle and now the right triangle with regular angles between 0 and 90 to define sine, cosine, tangent, and other trigonometric functions of any angle because you move around the circle. Okay, Elijah, what was your question?
I wanted to know how you got cosine and tangent for the last circle that you made, the bottom left.
What is the x coordinate of this point?
The x coordinate?
Yes.
Oh, it would be 3, 0, 3. Oh, sorry. 3, 2.
Okay, Elijah, I'll ask you an easier question. Oh wait, did everyone freeze?
Yeah, you're frozen on my screen.
Everyone's
Yeah,
Okay.
you're frozen.
I froze. Okay. All right. Let's try this again, Elijah. So what is the x coordinate of this point?
The x coordinate?
Yeah.
Would it be 1 then?
Of this point?
Oh, then it would be, 3, -3, my bad.
What? What are you talking about? No. This is a unit circle. This is 1. Don't look at the squares. I mean, okay, fine. I'll turn off the paper for you. Okay. What is the x coordinate of this point?
1.
-1. Okay. What is the y coordinate of this point?
0.
Okay, so there you are. Remember, the x coordinate is the cosine and the y coordinate is the sine.
Okay. All right, thank you.
All right, okay, someone else, Tasnimo, what were you saying?
Yeah, my question was for the special right triangles for 45 degrees, I thought
Yeah.
the sine and cosine was radical 2/2.
Yeah, and what did we get? This is the same thing.
Oh, okay.
Multiply the top and bottom by square root of 2, you're going to get the radical 2/2.
Okay.
Same thing. All right.
Mr. Scholar, wait, hold up. Scroll down a little bit.
Down or up?
Okay, up now, up. I just want to see what's below. Why is that in absolute value?
No, because sine theta could be positive or negative, right? Depending on which quadrant it lies in.
So all values can be positive or negative? Why?
Yeah, so once you let theta be not between 0 and 90, but any angle, the sine, cosine, and tangent could be anywhere, right? So if let's say your angle is, let's say, over here, then both sine and cosine are going to be negative because x and y coordinates of this point are negative, right? So you can still use a triangle. It's like if your point's over, if your angle is over here, right? You can still use a triangle to figure out what is the ratio, right? What is the sine and cosine? What is the coordinates of this point, right? But the coordinates are going to be negative. That makes sense?
Not really. I mean, is this just trying to show like reference angle or something?
All right. So if you have a triangle like this, right? Now let's say I tell you this angle, right? Will we be able to find the coordinates of this point?
Yes.
Right? You'll find this length, and you'll find this length, and then you'll be able to find what the coordinates of this point are, right?
Say that again. I didn't hear you.
So you'll be able to find the coordinates of this point if you know this length and this length, right?
Yes.
But the coordinates of this point are not going to be the same as the length, right?
Yes.
So that's why, like for example, the coordinates of this point is going to be the same as this length, and the opposite from this length, right?
So with this, we're just trying to find the length.
Well, so did you understand these examples that we did right here? Like when we tried to find the coordinates of this point, right? The coordinates of this point are negative square root of 2 over 2, comma square root of 2 over 2, right? So even though the sides of this triangle are square root of 2 over 2 and square root of 2 over 2, the coordinates of this point are not square root of 2 over 2, square root of 2 over 2. They're negative square root of 2 over 2 and square root of 2 over 2. Do you understand?
Yes. I just want to know why we would put sine into or all of them into absolute value.
Because sine of theta could be positive or negative, and sine of r can only be positive. You understand?
Okay, so we're trying to find the reference angle to get sine.
Yes, you find the reference angle, you find the sine of reference angle, then you determine whether or not sine of theta is positive or negative to figure out the sine.
And since this was negative, we have to put absolute value.
Well, I mean, I'm just saying this is a general statement, okay? Because you don't know if sine of theta is positive or negative. Yeah, the same was right. This is, I don't want to put plus or minus over here. Yes, putting absolute value is the same as saying sine of theta is, so because you have, essentially what we have is the following. You have sine of theta going to be equal to sine of r or negative sine of r, but you don't know which one. That's why I put the absolute value sign. Got it?
Got it.
Okay. So yeah, I mean this is just instead of just writing this whole thing, I just decided to write this. That's a cool one. Okay. All right. Okay. Now, here comes the calculus part. Because so far, at least in elementary school, we did it purple now. Okay. So you guys been doing you know, degrees, right? But degrees are actually very unnatural. Okay. Everywhere, like once you move on to like more advanced math, degrees just disappear. Nobody uses degrees. Okay. So radian versus degree measure. Okay, so how do we come up with the degree measure? Or whatever measure of an angle? Okay, so you take an angle, some angle, right? Let's call this angle theta. Let's say that the radius of the circle is r. Okay, now let's say the arc length over here is s. Okay, so what is the measure of the angle theta? I'm just gonna write theta. Okay, so we say that theta. So you say figure out what portion is s of the full rotation of the whole circle. This is the circumference 2 pi r. Is this okay with people? People need to remember the circumference of a circle is 2 pi r. Are we okay with that?
Yeah.
And we say that the whole circle is 360 degrees, and this is degree measure. For example, the right angle, right, would be a quarter of the circle, right? So this would be 1/4 of 360 degrees. Are we all okay with this? But if you instead say that the circumference of the circle is just 2 pi, you just get s over r, and this is called the radian measure. Radian measure is a lot more natural because notice that you have cancellation of 2 pi, so you just have s over r. You don't have any degrees. And the reason why it's more natural is because s is a length and r is a length. So the units of s over r, or of angle theta, are actually, it's dimensionless, so there are no units. Here, the units are degrees. Okay? So if your units are degrees, you cannot do arithmetical operations on theta. So for example, so advantages of radian measure. For example, sine of x squared is defined only if x is measured in radians. Okay? Because try to square 45 degrees. What is 45 degrees squared? That makes it has no meaning at all. You guys see that? Like, what is 30 degrees squared? It's 900 degrees squared. I mean, that's not an angle. That's like, I don't know what that is. Okay. All right. But then once this happens, you need to think of conversions. Okay. Conversion. Okay. So if you want to convert from degrees to radians, right? You need to multiply by pi, and you divide by 360. Sorry, by 180 degrees. So for example, if you have 30 degrees, it's going to turn into pi over 6. If you have 45 degrees, it's going to turn into pi over 4. If you have 60 degrees, it's going to turn into pi over 3. Okay. All right. Now, if you want to go the other way, you want to go from, let's say, radians to degrees, for whatever random reason that you might want to do that, but there's no good reason why you would ever want to convert back, but why not? You would multiply by 180 degrees over pi. It's like, I don't know, having, oh, you know, what is that currency? I don't know, having Russian rubles and converting them to dollars, and then deciding to convert back. Why would you ever convert it back? You know, you wouldn't do that. All right, anyway, so let's say you have radians and you want to convert it to degrees. And let's say we have, I don't know, 90. So let's say we have pi over 2 radians. In degrees, it's going to be 90 degrees. So let's say you have pi radians, and in degrees, it would be 180 degrees. Let's say I have 2 pi over 3 radians, and that's going to be 120 degrees, and so on, things like that. Okay? All right, so I think maybe I'm going to give you some assignments on that as well. Okay, so let me linger on this for a little bit and wait for people to ask some questions on this one. Are there any questions? Okay. Good. All right. Okay. So one last thing that people would need to know. Yeah, we're doing really well. All right. So another thing that people need to know is, since we define trigonometric functions for any angle, right? We need to talk about graphing. So graphing. There's also one more thing. There are also inverse trigonometric functions. So let's just yeah, graphing trigonometric functions. Okay, so let's say you want to graph y equals sine x. Okay, so how would you graph it? So you would, you know, you have axes, right? When you start plotting, so you just plot a couple of points. Sine of 0 is going to be 0. Maybe sine of pi over 3. So if you plot points, you end up seeing something like this. Some sort of shape like that. Okay, I'm not really super good at it. Okay, but this is this kind of shape that you're going to be able to see. Okay, it's going to be y equals sine x. In fact, if we go to Desmos, right? If we graph y equals sine x, this is what it's going to look like. Okay, and if we put a point, let's call this x comma sine x. Maybe a. Right, so if I move this point around, you see how it moves around the sine curve. Okay. So for example, if I let a is equal to, let's say, pi over 3. Here's the point when the angle is pi over 3. If I let the angle be equal to, let's say, pi over 4, here it is. If I let the angle be equal to, let's say, pi over 2, here it is at the very peak. Okay? And sine is periodic. Right? You see it like it looks exactly the same. Like if I move forward, right, it's just like a wave that keeps going up and down. Does anyone know why sine is periodic? Why does it happen?
Do you mean in terms of like the rotations?
In terms of angles, sure. Go ahead, explain that.
Oh, so like how you have pi over 2, pi over 4, and then pi. I'm not really sure what you're asking.
I'm asking this, like, you see, if you, let's say, have a is equal to pi over 2, or a is going to be equal to, let's say, a plus 2 pi, right? You see the value of sine, so even though the value of a is different, the value of sine of a is the same.
I think I know why.
Yeah, why?
Sine is showing you what would it be on a circle, but since you're putting it on a like I'll say a sine time graph or like I don't know something like that, you're just stretching it out, but really it's just moving in a circle, up and down.
Yeah, because if you think about it, right, think about a circle. Think about the unit circle. Let's say you want to evaluate, use the unit circle to evaluate let's say you want sine of, I don't know, 7 pi, right? Remember, full rotation is 2 pi, right? So how would you measure sine of 7 pi? So it goes 2 pi, 4 pi, 6 pi, 7 pi, right? Right. But notice that you end up, your terminal side ends at the same place as if you, this should be equal to the same as, let's say, sine of pi, right? It will be the same as sine of 3 pi, the same as sine of 5 pi, and so on. You guys see that? Rebecca, do you see this? No?
No.
Like how would you measure sine of some random angle? Like let's say you want, okay, so let me erase this. Maybe this is a little bit too much. So let's say you want sine of, by the way, are you okay with, radian measure? Let's say I put, let's say 3 pi. How would so I would need to measure angle 3 pi. Angle 3 pi lands over here. Okay? So it's the same as angle sine of pi, right? Because every time you do a full rotation, it's like you start from the beginning, right? Essentially, because of this property, you have sine of x is going to be the same as sine of x plus 2 pi, where 2 pi is a full rotation, right? 2 pi is like 360 degrees. So every 2 pi, so the period is 2 pi. So every 2 pi is like you're starting from the beginning, from 0, right? So that's why the sine graph is periodic. Make sense? All right. Same thing for the cosine graph. Cosine graph is also periodic. And if you look at the cosine graph actually looks exactly like sine, except it's shifted. right? Cosine x looks like this. Okay, exactly like sine, right? This is cosine and this is sine. Okay, exactly the same, except one is shifted. Okay, is this okay? All right, cool. All right. So we're okay with this, right? All right, so these are trigonometric functions. There's sine x and cosine x. Now there's also tangent of x, which looks really weird. Has a vertical asymptote. It looks like this. Okay. It's periodic, but it's weird. The reason why it has vertical asymptotes is because tangent is sine over cosine, and when cosine is equal to 0, tangent is going to be undefined because you're dividing by 0. Make sense? Yeah, that's why you have these vertical asymptotes. Okay. All right. Okay, so this is the crash course on graphing sine, cosine, and tangent functions. Now, I think the last, I'm not sure if it's going to be the last thing, but now we also have to talk about inverse trigonometric functions. So what are inverse trigonometric functions? So let's say you have a triangle, right? And let's say you want sine inverse of 1/2. What does that mean? This means that, what is this asking for? Find angle. Let's say you say sine inverse of 1/2 is equal to x. It says find angle x such that sine of x is equal to 1/2. Essentially, it's asking what is x such that its sine is equal to 1/2. So if this over here is x, then we're saying the sine is going to be 1/2, and this is going to be square root of 3. And hopefully people realize that this is a 30, 60, 90 right triangle. So sine inverse of 1/2 is going to be equal to pi over 6. Okay? This is how we define inverse trigonometric functions. Okay? So inverse trigonometric functions is essentially going in the opposite direction. So what is a trigonometric function? Trigonometric functions are functions where given an angle, it gives you a ratio. Now imagine you go in the opposite direction. Given a ratio, you want to find the angle. And that's what the trigonometric inverse trigonometric functions do. Does this make sense to people?
Wait, can you explain how you got pi over 6 again?
Well, I just know it. But it's like it's from special right triangle. Right? Because we want to find some angle x so that its sine opposite over hypotenuse is equal to 1/2, right? So if you draw this triangle, right, if this is 1, then this is 2, this is square root of 3, and you recognize this as your special right triangle, so this angle has to be pi over 6, or 30 degrees. Ariana, you on board?
Yeah, but is there a way that like we could find it like
In general?
yeah, like
No.
a
Calculator. Like you can't find the sine and cosine of any angle, like, you know, if I were to just randomly give you an angle, let's say I tell you find sine of, I don't know, 3 pi over 7. You would know how to do it, right?
Yeah, I think so.
I mean, how would you do this?
I'd change it into, well, I would change it into degrees.
Okay, sure, fine. Find sine of 31 degrees. How would you do this?
Well, I don't know anymore.
So you can't do it. I mean, you can do sine, cosine, and tangent for special angle, but if it's not a special angle, then you can't do it, right?
Okay.
So yeah, only a calculator. What you can do though is you can find trigonometric functions of inverse trigonometric functions. So what you could do is, here's an example. Let's say you want to find sine of cosine inverse of, let's say, 3/5, right? Now what this says is that this is some angle, right? So you have a right triangle here, like this. So let me make it to scale. Right, so let's say this is angle x, right? This is going to be x, okay? Cosine of this angle is 3/5, right? Now this is a 3, 4, 5 right triangle. This is 4. So the sine of this angle, you can see from the triangle, it's going to be 4/5. So you can figure out, like if you have inverse trigonometric functions followed by regular trigonometric function, then you can sometimes figure those out. Got it, Ariana? By just drawing a triangle. But in general, if you just have just have one of them alone, you cannot figure it out. Is that okay?
Yeah.
Okay, cool. All right, then here's what the graphs of them look like. Okay, so if you have, if this is tangent, right? Tan inverse. Well, actually, let me just call it arctan. Oh. Okay, this is what arctan would look like. Okay, so notice that this is just a reflection through the line y equals x. Okay, this is how okay, restricted. So that it's a little bit clearer. Okay, right. So I just restricted the domain for tangent, right? This is what tangent would look like. Okay, so the black one is the tangent. The red one is the tangent reflected through the line y equals x. Okay, because that's how you get the inverse of graphs. Okay, if you want,
Let's just go out. The black one is tangent and the red one is cos.
yeah, you can see from you know, from the left, right? Like on the left, it tells you right here, right? Tangent is black and the arctangent is red. Okay, now I'm going to turn them off, and I'm going to do the same thing for sine. Okay, notice for sine, I'm going to zoom it in a little bit. The sine inverse looks like only part of the sine graph, right? So, like if you were to take the sine graph If you were to reflect it through the line y equals x, you would have just this infinite curvy thing except along the y-axis, but that wouldn't be a function. So in order to make it a function, you restrict it to an interval, okay? And for arctangent, so arc cosine, right, it's also very similar, looks like this. So here's the cosine. I can change the color to something more acceptable. So here's the cosine, which is the purple one, and arc cosine is this part, okay? So arc cosine is only a small part of the rotation of the cosine x, okay? All right, okay. So this is essentially a crash course on all of trig. Okay, so let me go back now and let people ask questions. Okay. So, are there any questions about, like, oh, do you want to go through this again, the whole thing? Yeah.
Yeah.
All right. So we start by defining the trigonometric functions sine, cosine, tangent, secant, cosecant, and cotangent in terms of a right triangle. Right away, there's the Pythagorean identity, which so, okay, I'm mainly focusing on calculus right now. I'm trying to just cover the things which are necessary for calculus. In pre-calculus, there's a lot more stuff that we will cover. But for calculus, I'm just covering the main things because I don't want to overwhelm people. So for calculus, you need to know the Pythagorean identity, both of those two, right? You also need to know the special right triangles. Degrees you don't really need to know. You need to know it for radians, okay? So you need to figure out, know what the trigonometric functions of any angle are. So how do you, find them using a unit circle? And how do you convert from, like, what is the relationship between radian and degree measure? And how you can find trigonometric functions of, radian angles measured in radians. And finally, you need to know how to graph trigonometric functions and how, like, what we mean by graphing trigonometric function and graphing an inverse trigonometric function. Okay, and that's it. Okay, so this is like a crash course in trigonometry. There are other things, right, which I'm not talking about. For example, you can solve a trigonometric equation. Like, for example, you can solve something like this. So we're not talking about things like, let's say, sine of alpha plus beta, so sine of the sum of angles, or like solving, or like sine, or like maybe cosine of half an angle, right? Or, solving sine squared x plus, let's say, sine x, let's say -2 equals 0, something like this. Like something like this, right? We're not talking about solving equations like this, like trigonometric equations. Okay. There's other stuff which involves trigonometry, but it's not as relevant to calculus. Okay. All right. So hopefully, okay. So now that I gave you this crash course, when we touch upon this in calculus, I think it's going to be a little bit better, because I feel like so we're going to be doing trig next, like, and when we do trigonometry, people are going to understand a lot better what's going on. Because I don't want people to be like in the void and say, okay, what is sine, what is cosine, what is tangent? Now hopefully you have a better understanding of what they are. Okay. All right. Any other questions?
Can you scroll up a little bit, Mr. Sklar?
Yeah, sure. Like this?
Yeah, I just want to see the purple.
Yeah, sure. All right. Are there any questions? Oh no, I'll post this. I'll post this to breakout. Actually, I'm recording this. I'm also going to post it to the YouTube channel. By the way, all of you know about my YouTube channel?
Yes, sir. Already subscribed.
Yeah. Janae thinks it's hilarious that I have a YouTube channel. No, it's I think it's posted on Google Classroom, right? It's like it says videos, and I think it's there. Let me double check. But okay, but I think I should stop it since we're just chatting at this point. Okay, are we good?
I need to copy a little bit more.
All right, fine. I mean, yeah, I guess we're just chatting, but who cares? It's only for us.
So, Mr. Sklar,
Yeah.
for the triangle, if for the triangle top left, that's if the radius of the circle is 2.
Well, actually, this is a right triangle that you just create for specifically to find the angle whose sine is equal to 1/2. You can draw. See, remember how in the beginning is we said that you can draw any right triangle, and the trigonometric functions inside that right triangle. Like you can pick if as long as this angle is fixed, you can pick any size you want. The ratio of the sides is going to be the same. Could be here, could be here. So if I decide to make this side equal to 1 and this side equal to 2, right? Then this angle, the sine of this angle is 1/2. So this is a correct right triangle. So I can find the third side, and now you can actually recognize it as a 30, 60, 90 right triangle. Does that make sense? Or not really?
Yes. So you just made up the sides, right?
Yeah, I just created. I just picked the convenient sides. Make sense?
Yes.
Yeah. Okay. Yeah. So if you go to tutoring recordings on the classwork, I think there's a link right there. Okay.
Also, Mr. Sklar, you moved the date for the Albert IO homework, right?
Yeah, I need to do that. Sure, I'll do it.
Is it for
Okay,
both
thank you.
classes?
I'm sorry.
Is it for both first and eighth period?
No, the class. Yeah, the homework was the same for both classes. Yes.
Okay. So are you like changing the date for both classes? Because I'm in eighth period.
Yeah, sure. I'll change the date for both of them. No worries.
Thank you.
Yeah, and I'm also going to post an extra credit, I guess for all of you guys. We'll post an extra credit, maybe do Sunday or something on this, because you guys need a lot of extra credit. You guys need some help. So yeah, sorry. Yeah. All right. Okay.
Mr. Sklar,
Yeah.
can you show me the inverse graph again? I just want to get that down.
Oh yeah, sure. So this is the graph of okay. So this is inverse cosine and inverse sine. Okay, so the green is the inverse sine and the orange is the inverse cosine. Inverse tangent actually looks pretty cool. But
So the red is inverse tangent?
yeah, inverse tangent is like this. It's like if you zoom out, it's like actually really cool. It's defined for all values. You see, sine and cosine, right? They are defined only for values between -1. Arcsine and arccosine are defined only for between values -1 and 1. But arctangent is defined for everything. Yeah, Elijah, you can go. Now we're just chatting. All right. Okay. All right, we're all good? Yes?
Yes.
Oh, yes. I'm just getting this down.
Okay,
Yeah.
go ahead. All right. Okay, guys. So yeah, I think we're good. And yeah, I mean, I guess if you want to just stay and chat, that's fine. But if you want to go, you can go. It's fine. I'm not gonna show anything interesting. Okay. Vitus Nemo. I don't know. Maybe I'll say something. I don't know. Drop some knowledge. Who knows? Yeah. Yeah.
For tomorrow for parent teacher conference, like, can you just come anytime? I know, like, we had the
Yeah. I don't know. Don't tell your dad to come. He's fine. I was trying to call him twice and I couldn't reach him.
Oh,
You know.
Wait,
Yeah.
so-
It's
Wait.
okay. No, if he wants to come, he can come. But I mean, I don't know. I don't have anything to say about it. You're doing really well, so you can just tell him that.
Wait, Mr.
Yeah.
Shepard, did you call my parents already, or do I have to make them come tomorrow?
Let me check. Give me a second. Well, I mean, do your parents remember if I talked to them?
Uh,
I mean, I'm just curious.
I don't even know. I don't even know if my mom received the call or not.
I mean, how can your parents not remember? Like, they talked to me, like, I wonder.
I don't
Right.
know. I just because I didn't sign up. I didn't know. My mom didn't sign up for it yet, so I just need to know if she needs to or not.
No, I didn't talk to your parents yet. So, no, I mean, if they want to talk to me, they can talk to me. It's not like a mandatory thing.
Wait,
But
what?
it's not mandatory. Like, your parents don't need to show up. It's not like you have to do it. But it's only if your parents want to find out how you're doing in class,
Oh, okay.
right? I mean, so yeah.
Wait, Mr. Scar, did you call my mother?
I'm sorry?
Did you call my mother?
Did I call your mother? No, I
Oh,
don't
yeah.
think so. I mean, yeah, I don't think so. But yeah, because you're doing well, I was calling. You were not in like my high priority list. So
Mr. Sklar,
yeah,
you scroll up to the very first page we did.
sure. All right, here you go. Yeah. Okay. Uh-oh. Oh no, I thought this. Oh, Natanya is here. Natanya, you're a little bit late to the party.
Yeah, I just woke up.
Well, hello, Natanya. Hope you're.
Hi.
We're kind of finishing up now. Well, anyway, I'm going to post this on. I'm going to post the video in the notes, so you can
Subscribe to his
take a look.
YouTube channel. He needs more followers.
Nah, don't yeah. Subscribe and like, right? Like and subscribe. Click that like button, right? Comment below, right? All right, okay. Are we good? Is everyone okay? All right.
Almost done with this slide.
You almost done? Okay. All right. Well, anyway, guys, the rest of you can, yeah, I don't know, we're just gonna chill with James.
All right, bye, Mr. Shackler. Have a good day.
All right, okay.
Goodbye. Have a good
Okay.
night.
I came so late. I came at the end of this whole thing. Oh my gosh.
Yeah, I don't know how you managed, like, we're,
I
well, I
went
mean,
to bed as soon as school was over and I just woke up.
yeah, I did that too, but I set my alarm, so I woke up, so I would teach you guys, you know. See, I was sleeping, I was like enjoying myself, I was sleeping, and I'm like, now I need to teach them, and then I got up. That's how dedicated I am. You know?
I feel so bad because I promised myself I'd come and then I fell asleep.
Yeah, well, watch the video then, okay? All right, see
You
you,
did make
Amalia.
it, Tanya.
Mr.
You are
Sklar, can you
here.
scroll down a
Just
little
at the
bit.
end.
Scroll down, yeah, sure.
I did make it, right, Janae? Yep.
Yeah, no, yeah, Natanya, just take a look at, okay, now I'm gonna stop the recording.
Go down a little bit more.